Okay, so vectors. Talked about a little bit today in class. A vector is something that has both a quantity or a magnitude and it has a direction. So we gave examples today of things like displacement, like how something has moved in space, velocity, how fast it's going and in what direction, acceleration, how something's velocity is changing and in what direction, and force, which we will get to later, and that is how hard something is being pushed or pulled, and again, in what direction. Vector quantities are sort of contrasted with scalar quantities. A scalar quantity is something that just has a magnitude. The most common ones we will see in physics this year are time, mass, and if we get to it, energy. So, get my device to work here. One of the key ideas about vectors, one of the things that's kind of cool about them, is you take a vector, so as long as you have vectors that represent the same thing, so let's imagine that's a displacement vector, and then I have a second displacement vector, and then maybe I have a third displacement vector, and a fourth displacement vector. As long as I stack these vectors on top of one another, it's sort of this head to tail idea. So each tail connects with each head. I just keep stacking them. Then the sum of those, if I add all of those vectors up, so you could say that this is an example of like you walk in this direction, you walk this direction, you walk that direction, you walk that direction. Where do you actually end up would be what we call the resultant vector. And that resultant vector is always going to be, oh, sorry, that did not do what I wanted it to do. It's going to basically be start at, obviously, the start, which is where that initial vector began, and end up at the tip of the last vector. Now, this would be true also if these were velocity vectors, which would be kind of weird, but imagine we're adding up a bunch of velocities. The other thing that's kind of crazy is it doesn't matter what order you add them in. So let's imagine that this was my first one, and then this is my second one, and then let's say this, oh boy, let's not do that because I just changed the size. This is my third one, and this is my fourth one. It works out that still my resultant, which is the sum of all those vectors added together, is the same. It still works out no matter what order, what sequence I put them in. So these little vectors that we're adding up, these things are called components, vectors. The ones that we're kind of adding up, they make up these little bits and pieces, and then the red vector here, that is the resultant. So as we saw today, sometimes, and most times, it's handy to use trig, since these things, we work with angles and stuff like that. If I have a vector in, oh, sorry, change color here for a moment. If I know that I have a vector that is moving in some direction, so I say, we have a boat. Let me back up here. We had an example where there's like a river, and we know that someone is trying to swim across that river with some velocity, and we know the river also has some velocity, then we can figure out their resultant velocity through vector addition. So if we know the quantities of each of them, if this is A, this is B, then C is equal to, through Pythagorean theorem, C is equal to the square root of A squared plus B squared. And then if we know one of these angles, or then once we know one of the quantities, we can calculate this angle. We can say with great certainty that we know exactly what that vector C is. We know its quantity and we know its direction. In this case, we know that the tangent of that angle is equal to our opposite, which is B, over our adjacent, which is A, and therefore we know the angle is equal to inverse tangent of B over A. So now we can clearly describe both the magnitude of the vector and its direction.